Good afternoon viewers and welcome to the EduSat lecture for the science stream. Today we are on the third lecture for the chemical thermodynamics and we have with us Dr. Amit Kumar from the Dayal Singh College. We have been learning about the first law of thermodynamics, we have done the second law of thermodynamics and we have done a detailed study on entropy. In today's lecture, we will be studying about entropy in terms of state functions. So over to Dr. Amit Kumar.
Thank you very much, Unnati. First of all, I wish very good afternoon to all the viewers, dear friends. As it has been already been observed that what we have covered till the point of time regarding entropy also. Now, we would like to start from where we left in the previous lecture. That is where we were discussing how we can make use of thermodynamic definition of entropy, that is to calculate the entropy change accompanying the phase transformations, because phase transformations are constant temperature processes. So these are isothermal processes. So such isothermal phase transformation processes, we can make use of the thermodynamic definition of entropy directly and we can relate it to change in the state variables we have already observed. So in general, let us have a look at the delta S trans. This represents the entropy change for a particular phase transformation, that equals to delta H, the enthalpy change for a particular phase transformation divided by its temperature of transformation, transition temperature. So in that way the transition can be vaporization, fusion or sublimation. Now till the point of time in 12th standard also, students would have been conveyed that entropy changes in the order that entropy associated with gaseous species are greater as compared to liquids and they are having greater entropy as compared to solid. Now, why and how this observation is made? This is basically a consequence of this second law of thermodynamics in itself. Just have a look at the equation once again. Now, if we consider the fusion process, it is basically the phase transformation from solid phase to liquid phase, and the vaporization is the liquid phase to vapor phase and the sublimation directly from solid phase to the vapor phase. So, when we want to calculate entropy changes for these phase transformations, straight away we need to apply this formula, that is entropy of transformation, that equals the enthalpy change by the temperature at which the transformation occurs. Now, considering the fact that what is sublimation? Sublimation is basically the process in which a solid substance directly converts to its vapors. So, therefore, the enthalpy of sublimation would be actually the enthalpy of this molar enthalpy of the substance in vapor phase less the molar enthalpy of the substance in solid phase. Same thing can be obtained as sum of two enthalpies, that is the enthalpy change accompanying the fusion process of same substance, added to which is the enthalpy change accompanying the vaporization process of the same substance. So, therefore, what we get is enthalpy associated with the vapor phase will be highest and that of the solid phase of same substance will be lowest, and in between would lie the liquid phase. So, accordingly, if we look at this delta S transformation formula, it straight away gives us an idea that entropy, molar entropy associated with solid phase would be much less as compared to molar entropy associated with liquid phase, which will be further lesser than that of molar entropy associated with vapor phase. So, it is very clear from this application of this formula itself, that is a consequence of thermodynamic definition of entropy coming from second law of thermodynamics. It becomes very clear that entropy associated with gaseous phase is higher as compared to liquid phase, and liquid phase if we compare with that of solid phase, the entropy would be the least value associated with the solid phase. Having said this, now coming over to the fact that what help in addition this formula can lend us. Basically, this formula also leads to an important rule, that is called Trouton's rule. What actually is a Trouton's rule? It was observed when the entropy change for vaporization of various substances was calculated. It was observed that for many substances the entropy change of vaporization process almost comes very near to a particular value that ranges somewhere in between 88 joule per Kelvin per mole to 90 joule per Kelvin per mole. This was the observation. This observation led to the conclusion. That conclusion now is most popularly known as Trouton's rule, according to which we can approximate the entropy of vaporization of substances. That is, according to this rule, the approximate value for the entropy change accompanying the vaporization process, the molar entropy change, that is approximately its value comes out to be 88 to 90 joule per Kelvin per mole. That is what is Trouton's rule. Now, if there are certain exceptions regarding the applicability of Trouton's rules on various substances also. What are the exceptions? There are exceptions of those substances for which the vaporization temperature, their boiling point lies below or at about 150 Kelvin. These are those substances which does not follow Trouton's rule. Moreover, Trouton's rule is also not followed by associated liquids. What are associated liquids? Associated liquids are those ones, for example, water. Water, if we consider, that is a very small molecule. It should not have been at usual temperature pressure condition, that is normal conditions, 1 atmosphere pressure and 25 degrees Celsius temperature. At this temperature pressure condition, water, considering its very small molecule, it should not be in liquid phase, but it is in liquid phase just because of the hydrogen bonding. A large number of molecules are arranged by, are in bound state by virtue of hydrogen bonds. So, therefore, we consider such liquids as associated liquids, and for those liquids also it has been observed they also do not follow the Trouton's rule. So, these are two exceptions to the rule, those liquids which are associated liquids and those liquid substances for which their boiling point lies at 150 Kelvin or somewhere below 150 Kelvin, they are not found to follow the Trouton's rule. But what implication the Trouton's rule have? Just have a look. If suppose some substance follow Trouton's rule, it straight away means that molar entropy of vaporization would be very close to 90 joule per Kelvin per mole, and molar entropy of vaporization equals to molar enthalpy of vaporization divided by its transition temperature, or in other words the boiling point. So, if for a liquid we know its boiling point, then we can get to its molar enthalpy of vaporization straight away if a liquid follows the Trouton's rule. Just have a look. With the help of a illustration we can see molar enthalpy of vaporization that just approximates to 90 joule per Kelvin per mole, that is molar entropy of vaporization. We need to multiply it with transition temperature, that is the transition is vaporization that is occurring at its boiling point of the liquid. So, if we know the boiling point of a liquid if the liquid follows the Trouton's rule, from which we get to know its molar entropy of vaporization, we multiply the two quantities, what we get is molar enthalpy of vaporization. So, this is another application where this equation actually finds application and help us to know the molar enthalpy of vaporization. Now, question arises, does this as the Trouton rule exists for vaporization process, does there occur some other rule, similar kind of rules are also available for fusion process? The answer is simply no. There is no such rule for fusion process, there is no such rule for sublimation process. But yes, what we can say one thing about the fusion process, that for most of the substances for the fusion process, the range of molar entropy of vaporization lies somewhere in the range 1 R to 4 R. What is R? R is gas constant, whose value is 8.314 joule per Kelvin per mole. So, therefore, molar entropy of fusion process for most substances would lie somewhere between 8 to 32 joule per Kelvin per mole, that is 1 R to 4 R. For example, if we consider the metals, the constituent particles in metals are atoms. So, for such species, it has been observed that the molar entropy of vaporization lies very close to 1 R, that is 8.314 joule per Kelvin per mole. This is an experimental observation. Now, coming over to those substances which are very large in nature, for example, long chain hydrocarbons, for example, polymeric substances for which this molar entropy of fusion can also go up to 15 R, where R is again gas constant, whose values is 8.314 joule per Kelvin per mole. Right. Having said this, and considering this application to fusion and vaporization process, and how the second law reveals us the value of molar entropy of these phase transformation, now it is turn to again consider the thermodynamic definition of entropy. See, the entropy is defined by the differential equation ds equal to dq reversible by T. This equation, as we see, relates a path function, that is a heat involved in being exchanged by the system with the surrounding, and where we make observation about the path function, we make observation about the path functions in the surroundings only. So, therefore, this equation relates the change in entropy with the effects dq reversible observed in surroundings. So, idea is that we do not want us to be dependent on those properties which are path functions, or where we need to constantly make observations in the surrounding while the system undergoes transformation. All we need is, we need to transform this thermodynamic definition of entropy in a way that it just relates the change in entropy with that of change in state functions. So, therefore, this becomes our next objective, to see how the entropy change can be quantified with the change in state functions. For which, let us now consider that if we have a system, it would be certainly having its values of state properties such as volume, the temperature and the pressure. Now, considering the fact that the system is capable of only expansion work, no other kind of work the system can do. If it is so, then expansion work is also can be done only reversibly. If the system is capable of only doing expansion work, that too only reversibly. And we all know, let us once again remember the characteristics of reversible expansion, as I conveyed you in my second lecture itself, that for a reversible expansion, it is very important that there should be a only infinitesimal difference between the internal and external pressure of the system, and therefore, for all practical purposes, we can say the expression of work which is equal to P op, that is opposing pressure, times dV, where we can replace P op with P, the internal pressure of the system. The reason being that there is only an infinitesimal difference between the internal pressure and the external pressure. So, therefore, instead of writing P op dV for the work expression, we can write P dV. So, therefore, these are our assumptions about the system, that it can only undergo expansion work, no other kind of work the system can undergo. Moreover, whenever it undergoes expansion work, it can do only reversibly. So, in that case, P op becomes P, and therefore, W becomes P dV. With that, the first law equation transforms to dq reversible equal to du plus P dV. If you remember, we had this first law expression after substituting the value for the work expression. Having said this, now if we divide this equation 9, which is basically the first law of thermodynamics, if we divide this equation with temperature, what we get? dq reversible by T equals to du, that is 1 by T du, plus if we divide P by T, so P by T dV. So, this equation 10 then becomes the transformed equation of first law of thermodynamics if we divide the equation 9 by temperature. Now, if you notice, what is at the left hand side? dq reversible by T, what it is? It is ds, the infinitesimal change in entropy that comes from second law of thermodynamics. So, we substitute that, and here in equation 10, what we get is equation 11, where it relates the change in entropy of the substance with the change in internal energy and the change in volume. What is internal energy? Isn't it a state function? Answer is certainly yes. So, what is volume? Isn't it a state function? Again, the answer is yes, it is. So, therefore, what we have developed is, we have developed an equation which relates the change in entropy with the change in state functions. One is the energy, internal energy, and the other is volume. And more importantly, the differential coefficients are also state functions. For example, temperature is a state function, pressure is a state function, temperature again is a state function. So, therefore, in this equation 11 which relate the entropy change, it relates only to the change in state function. Moreover, the differential coefficients are also state functions, state properties of the system, which we can easily measure. But the question is, what about du? The change in internal energy, it is measured, but with little bit of difficulty. So, moreover, let us consider this equation 11 again before proceeding little further. In this equation 11, do not you think that it is an equation which is resulting from combination of first law and second law of thermodynamics? So, therefore, we say it is the equation resulting from the combination of first and second law of thermodynamics, where dq reversible has been replaced with the help of second law of thermodynamics in first law equation with ds, and therefore, this equation is called as fundamental equation of thermodynamics. And that equation is very important for discussion of equilibrium properties. So, a combination, this is again, let me emphasize that this is a combination of first law and second law of thermodynamics, and let me read it. ds equals to 1 by T du plus P by T dV. Right. Having said this, now the question arises, in the laboratory if you look at it, do you think we have a control, which are the variable we have a control over? We have control over temperature, which we can easily control just by heating or cooling some systems. We have control over volume also, that is, we can control the volume of the system also. If such cylinder piston system arrangement has been there, we can also control the pressure also. So, which are the variable we can control? We can control temperature, we can control pressure, we can control volume. More importantly, the temperature and volume. Less importantly is the pressure. It is a very difficultly controllable, but yet we can control it. But the question is, the internal energy we have least control. So, therefore, if we have in our equation which relates the entropy change with the change in state variables such as internal energy and temperature. So, you see here the internal energy where we have least control. So, it would be little difficult for us to calculate entropy change using this fundamental equation of thermodynamics. So, all we need to do is we need to modify this thermodynamic equation of this fundamental equation of thermodynamics in terms of by replacing or expressing change in internal energy in terms of change in temperature, volume, pressure, because we all know that internal energy again is a function of state variable, the temperature and pressure, volume and pressure. So, let us see how we do that. Now, consider entropy, which has been a function of temperature and volume. So, we can write S is a function of temperature and volume, and when this is so, we can write the infinitesimal change in entropy S ds, that is ds equals to, first we need to write rate of change of entropy with temperature, that is del S by del T, keeping the volume of the system constant. So, this is the first differential coefficient. Now, this is the rate of change of entropy with temperature. When we multiply this rate of change of entropy with temperature with total temperature change at constant volume, we get the contribution of when the temperature changes. The first part actually describes the change in entropy due to temperature change alone. Now, considering the second part in equation 12, it is rate of change of entropy with volume at constant temperature, that is del S by delta V at constant T multiplied with total volume change. So, therefore, the second part expresses the change in entropy as a result of change in volume alone, keeping the temperature constant. Now, if we want to calculate entropy change from equation 12, we should have the value of differential coefficients, that is delta S by delta T at constant V and delta S by delta V at constant T. Entropy we have just defined. So, it is like a catch-22 situation. Entropy we have just defined, and we are trying to find its relationship where it changes. We are looking for expressing a rate of change of entropy with temperature. So, this catch-22 situation which has arisen out of this simplification which we have tried to introduce we can get rid of. If we find some equation like ds equal to a dt plus b dv, where a and b just represents some properties of state of system, so that we can straight away say this differential coefficient delta S delta T at constant V is just this property A, whose value we know, and we can substitute in this equation and we can get to know these differential coefficients values, and by virtue of knowing A and B values of state properties of system, and we can get to know the entropy change. So, now if we want to find such an equation, that is ds equal to A dt plus B dV, we need once again to appeal to fundamental equation of thermodynamics. The fundamental equation of thermodynamics says ds equal to 1 by T du plus P by T dV. It is like dV is common, so differential coefficient, the second term delta S delta V constant T equals to P by T, that can be evaluated, but the second term contains du, not dt. So, therefore, this equation cannot be used to evaluate these differential coefficients. So, we need some modification. What modification we can look for? We should look for some modification in a way that this change in change in internal energy, which is being shown here in fundamental equation of thermodynamics, we can express it in terms of temperature change and volume change, for which let us consider internal energy as a function of temperature and volume. So, therefore, we can write the change in internal energy as rate of change of internal energy with temperature at constant volume times the change in temperature. Similarly, rate of change, the second term we can write as differential coefficient delta U delta V at constant T times dV. So, this is equation 13. So, equation 13 here we can modify. We all know what is heat capacity. Heat capacity at constant volume, basically, that is given the symbol Cv. What is this heat capacity at constant volume? Isn't it the heat exchanged by the system under condition of constant temperature for unit rise in temperature? That is heat absorbed by the system for unit rise in temperature at condition of constant volume. So, if this is so, that the equivalent expression is also delta U by delta T at constant V. So, instead of this differential coefficient which is figuring in equation 13, we can just substitute Cv. So, our equation 13 then transforms to du equal to Cv dt plus delta U delta V at constant T dV. Now, this is how we get equation 15. Now, the idea is that we once again look for fundamental equation of thermodynamics, that is equation 11, where du we have, and in the left hand side of equation 15 we have du. So, we can substitute the expression 15, that is the value of du from equation 15 in equation 11. So, what we get is ds same here equal to 1 by T same here, and instead of du we can write in square bracket Cv dt plus delta U delta V at constant T dV, added to which is the second term plus P by T dV. Having said this, we can expand it out of its brackets. So, what we get ultimately is ds equal to Cv by T dt plus 1 by T delta U delta V constant T dV plus P by T dV. So, this equation 17 is a modified form of equation 11, that is fundamental equation of thermodynamics. So, equation 17 is again the same form of it is the same fundamental equation of thermodynamics, but we have just modified it in terms of temperature and volume. So, now you can see we can collect those terms together which have same differential, that is dV, and those terms which have same differential dt. So, Cv dt is the only term which have differential dt, and these two terms have differential dV. So, we can take dV common, and 1 by T is also can be taken as common. So, 1 by T within the square bracket we have two terms P plus delta U delta V constant T dV. So, this is again equation 18 is again a modified form of fundamental equation of thermodynamics, but now instead of du we have got it in terms of dt. So, now see the equation 18, what we can compare it with? We can now consider equation 12, which we had envisaged for entropy change, that is ds equal to delta S delta T constant V dt plus delta S delta V constant T dV, and the equation 18 which we have just proved, that is ds equal to the modified form of fundamental equation of thermodynamics, that is ds equal to Cv dt Cv by T dt plus 1 by T P plus delta U delta V constant T dV. Now, can we compare the two equations 12 and 18? Yes, of course we can, because both these equations have same differential coefficients dt and here also the dV. If so, we can say these differential coefficients which we cannot evaluate experimentally. So, we have made a method theoretically of evaluating these differential coefficients delta S delta T constant V and delta S delta V constant T. That becomes, by comparing the two equations, becomes equal to Cv by T delta S delta T constant V and delta S delta V constant T becomes P 1 by T P plus delta U delta V constant T, like this. So, this is how we have theoretically derived expression which relates the quantity, the desired differential coefficients with experimentally measurable quantities like heat capacity at constant volume. It is very easily measurable experimentally, the temperature of the system easily measurable. Again here, if this differential coefficient we see, temperature is easily measurable, pressure is easily measurable, but here there is a problem. This is, if you remember, Joule-Thomson coefficient had revealed us the value of this delta U delta V at constant T. So, this is a little difficult process. So, we would to evaluate this differential coefficient. So, first one is okay with us, that is, we have just got a very simple expression for this differential coefficient in terms of just heat capacity divided by temperature, but for the second one we need further modification, that we would like to see what way we can. For the time being, if we want to further emphasize the first differential coefficient, how we can make use of this differential coefficient to calculate entropy change, let us see. Delta S delta T constant V equal to Cv by T. So, which we can rearrange, what we get is, we can take the denominator of left hand side dt to the right hand side numerator. What we get, ds equal to Cv by T into dt. Now, we can integrate this equation 21 within limit temperature 1 to temperature 2. So, what we get is S2 minus S1 at the left hand side, that is finite change in entropy, which is represented as delta S. So, delta S equal to integral T1 to T2 Cv by T dt. If our heat capacity at constant volume is independent of the temperature range in which we are working experimentally, then in that case we can take Cv out of this integral, and when we take this Cv out of this integral, what we are end up with is integral dV by V within limit T1 to integral dt by T within limits T1 to temperature limit T1 to T2. So, what we get when we integrate this expression, we get simple expression delta S equal to Cv ln T2 by T1. So, this is a very simple expression. All we need to do is we need to know the heat capacity at constant volume of the system, and we need to know that temperature after the change has been made, the system has undergone some change, and the initial temperature also, initial and final temperature if we have, heat capacity, constant volume we have, we can easily quantify the entropy change in terms of temperature change, provided the volume is kept constant. So, now idea is we have evaluated the first term, that is the entropy change due to temperature change alone, keeping the volume constant. Now, our next objective is to quantify the entropy change for a particular change in volume at constant temperature, so that we can add the two terms and we can quantify the total change in entropy. But as I have already specified that evaluation of our second differential, let us again have a look at it. It is little difficult because it contains the term corresponding to delta U delta V at constant T. So, therefore, we need to simplify this expression. What way we can do that? We can make use of the differential coefficients again, and we can make use of the properties of state functions, that is their cross derivatives are same. What we mean by saying this? Just have a look. If we consider a state function f, then its double differential, second derivative with respect to the two different variables with respect to which that function is being differentiated. The idea is that when we say cross derivatives are same, this is, we also covered this aspect, we also covered in our second lecture. So, this is the just I have written the formula which we had proved, that is del square f by del x del y equals to del square f del y del x. That is, if there occurs a state function f and is a function of two variables, and if we differentiate this function with respect to both the variables, the order of differentials does not matter. That is what the cross derivative same condition means to us. We can make use of this mathematical relationship that is called Euler's theorem. We can make use of this Euler's theorem in order to explore our second differential coefficient in the entropy change expression. Just see how we do that. Again, consider the first differential coefficient delta S by delta T at constant V equal to CV by T. What we need to do is, we need to differentiate it, this equation 19, with respect to volume at constant temperature. What we will get is del square S. First S will be differentiated with temperature as is written in equation 19, and then this expression will be differentiated with respect to volume at constant temperature. So, therefore, what it means, this equals to this CV by T, it means we need to differentiate CV by T with respect to volume at constant temperature. Since the temperature is kept constant, so this 1 by T we can take it outside and we can differentiate CV. What we get is 1 by T delta CV by delta V at constant T. So, but the question is, what is CV? CV we can, I just showed you that CV can be expressed in terms of rate of change of internal energy with temperature. So, CV equals to delta U delta T constant V. So, we can just substitute in this expression. What we get? 1 by T del by del V delta U by delta T at constant V at constant T. It means first you differentiate internal energy with respect to temperature at constant volume, then you differentiate whatever you get with respect to volume at constant temperature. So, therefore, this is again the same equation I have written at the top. So, what it does mean? The left hand side is being the same, del square S del V del T equal to 1 by T del, we can just write this expression as del square U by del V del T. That is, the first internal energy is being differentiated with respect to temperature, then with respect to volume. So, this equation 26 is an important equation. Why it is so? That will be highlighted upon a little later from now. Now, let us consider equation 20. Just what we did, let me sum up again. What we did is, we did consider equation 19. This was basically the differential of entropy with respect to temperature, and we differentiated it with respect to volume at constant temperature. So, now we consider equation 20. Basically, this is just nothing but is a differential of entropy with respect to volume. So, what we need to do is, we need to differentiate this expression with respect to temperature at constant volume. So, what we get is we get del square S by del T del V. That is, you see here del S by del V means it is first differentiated with respect to temperature, and then when we say del square as del T del V, it means second time we differentiate this differential coefficient with respect to temperature at constant volume. So, therefore, it means we need to differentiate right hand side expression with respect to temperature now at constant volume, which we have just written symbolically as here in a jugglery of few bracket terms, like del by, it means del by del T, that is differential of this whole expression 1 by T P plus del U by del V at constant T, and this differential should be done at constant volume. That is what we mean by writing so many bracket terms over here. Again, considering the same equation, now let us differentiate it. We would differentiate it as byproduct using making use of the product rule. We will first of all, because here temperature is a function of temperature straight away, which we with respect to which we are differentiating. So, P plus del U by del V at constant T, this also become a function of temperature. So, this is how we will differentiate. We will consider 1 by T as one function and P plus del U by del V at constant T as other function, this bracket term, this whole bracket term. So, therefore, let us first of all write just 1 by T as such and differentiate this within bracket term first. So, the first there is pressure. So, we need to write its differential as del P by del T at constant volume, plus we need to differentiate this differential coefficient. It has already been, it is this differential coefficient is just been the differential of internal energy with respect to volume at constant temperature. So, now what we need to do is we need to differentiate this differential coefficient with respect to temperature at constant volume. So, what we will get del square u by del T at del T del V, and then we will write the second this function p plus del u by del V at constant T as such, and then we will multiply it with the differential of the first function, that is 1 by T. What is the differential of 1 by T? Minus 1 by T square. So, therefore, we just write over here minus 1 by T square and second term P plus del u del V at constant T as such. Again carrying forward with equation 28, this is just. So, here now idea is that this is equation 28 we got. If you remember, equation 28 we got when we differentiated equation 20 involving one of the differential coefficient with respect to temperature, and equation 26 we got when we differentiated first differential coefficient with respect to volume. So, ultimately what we get is in the left hand side of the two expressions as second derivatives of entropy, but with different orders. One is del T, that is first volume, one in which the entropy is being differentiated first with respect to volume, then with respect to temperature, and in the other the entropy function is being differentiated first with respect to temperature and then with respect to volume. So, we get these two equations which we can compare, the equation 28 and 26. If you notice, as we just said Euler theorem, that if there is a state function, then its if we consider its second derivative with respect to two different variables, the order of differential is immaterial. When we say so, it does mean that when the order of differential is immaterial, what it does mean that we can compare the two equations and we can equate the right hand side of both the equations, because left hand side is just been the same, because the order of differential is just been the same, making use of Euler relation. If we do so, what we get is this expression. This is a big expression we get. This is the right hand side of one equation and this is the right hand side of the other equation, and we equate them two. If you remember, here we have 1 by T del u by del V del T equal to 1 by T del P del T at constant V plus del square u del T del V minus 1 by T square P plus del u del V at constant T. Here there is a term, the second derivative of internal energy. Here also in the left hand side also there is second derivative of internal energy, but their orders are, order of differentiation is different. First, here it is first with respect to volume, then with respect to temperature. Here it is first with respect to temperature, then with respect to volume. So, in this next equation, what I have done is, here instead of writing dt dv, I have written dv dt, because order of differential is immaterial, again using the Euler relation. So, therefore, these two terms do cancel from left and right hand side. What we end up with is 0 equals to 1 by T del P del T constant V minus 1 by T square, this term P plus delta U delta V constant T. So, this is our equation 29. What we get from equation 29 is, we take one term, this term, to the other side. What we get, 1 by T del P del T at constant V equal to 1 by T square P plus delta U delta V constant T. Now, having said this, we can take this T square, we can cancel 1 by T from both the side. What we get is 1 by T will remain here, P plus delta U delta V constant T, that is equal to delta P delta T constant V. We get equation 30. This is a very important equation. What way it is important, we just get to know from the next slide. You see here equation 30 is this, which we had just derived, and now if you remember what is equation 20, the second differential coefficient, which I said it is little difficult to determine because it involves the term delta U delta V constant T. This term is little difficult to determine. So, what we have done is, this differential coefficient which was figuring in the entropy change expression, which was expressed in this term, we have now got equation 30 which also expresses this term, but in terms of some easily determinable differential coefficient, that is del P del T at constant V. So, by comparing equation 30 and 20, what we get is just simple, delta S delta V constant T equal to delta P delta T constant V. This is what as an expression we get. Now, what this expression relates, it is important to note and make an observation about entropy. It is not an experimentally determinable quantity. What I mean to say is there is no instrument which reads entropy for you. What we can measure experimentally, we can measure only temperature, pressure and volume. These are the experimentally determinable quantities, and which we relate them to changes in other state functions such as internal energy, such as enthalpy, such as entropy and so on. So, this equation 31 is a very important equation. What way it is important? It relates the change in that property which we cannot directly determine experimentally with change in those quantities which we can determine experimentally, like the change in pressure and the change in temperature under condition of constant volume. So, therefore, what we get is this equation, again I have written, this equation is relatively simple expression for the isothermal volume dependence of the entropy. This is how we would like to read this term. We should understand what way we should read the mathematics, read the equations. The left hand side of this equation represent the isothermal volume dependence of the entropy. That is, it relates one differential with that of the other. It means it relates the change in one property with that of the other. But the question arises, the right hand side also does the same, or can we express this right hand side in some other quantity? That also needs to be seen. Anyway, we will just talk about it. Now, this right hand side quantity is very easily determinable. If you remember, in our first lecture itself, we talked about cyclic rule, and we talked about there then that if three variables are related in the form of a cycle, such as pressure, temperature, volume, all three are related, then there is a relationship that del P del T at constant V into del T del V at constant P into del V del P at constant T equal to -1. Using that expression, that is cyclic rule, we say, if you remember, we also had derived that del P del T at constant V equal to alpha by kappa. What is alpha and what is kappa? We also, if you remember, we also had defined there. Alpha is basically the expansion coefficient, that is 1 by V del V by del T at constant P. And what is kappa? Kappa is the coefficient of isothermal compressibility, and alpha is expansion coefficient, kappa is coefficient of isothermal compressibility. So, these are experimentally determinable quantities. Alpha represents what way the volume changes with change in temperature. Volume change we can easily ascertain experimentally, temperature change we can easily ascertain experimentally. So, alpha we can easily determine experimentally. Same way is the kappa. Kappa is the compressibility factor. All we need to know is how the volume changes with change in a particular change in pressure, and therefore, both these alpha and kappa are experimentally determinable quantities. Moreover, it is important to note that if you remember also again that kappa is always positive. That is, if we increase pressure on the system, volume will always be a negative, volume will always decrease. So, therefore, expression of kappa is minus 1 by T del V by del P. So, if del P is positive, del V is negative, negative multiplied with negative become positive. So, kappa will always be a positive quantity, that is isothermal coefficient of isothermal compressibility, kappa will always be a positive quantity. Now, question arises, what about alpha? Will that be always a positive quantity or not? Answer is that alpha for most of the substances will always be a positive quantity. That is, if we increase the temperature, the volume will always rise, but there are certain exceptions to this general observation also. For example, water itself. If you remember, you would have studied in your 12th standard textbook itself from a range between 0 to 4 degrees Celsius temperature. The water basically, for water, instead of having observation such that with increase in temperature, with we observe a increase in volume, we observe a decrease in volume. That is because of the extent of hydrogen bonding, which decreases with increasing temperature in this temperature range particularly. So, as I said already that water is an associated liquid, and by virtue of this change in extent of hydrogen bonding within this particular range of temperature, we observe instead of an increase in temperature because of a change in temperature, because of an increase in temperature, we observe a decrease in volume. When we increase temperature of the system, instead of observing a increase in volume, that is, once again let us consider, if we increase temperature, the volume rather than showing an increase shows a decrease within the temperature range 0 degree Celsius to 4 degree Celsius for water. And I just also explained why this occurs, just because of the change in extent of hydrogen bonding, and therefore, by virtue of hydrogen bonding, it is only the open structure and the molecules do come close, and as a result volume decreases. Anyway, so in that situation, for such liquids, antimony is another example for a particular temperature range for which alpha is also negative. Bismuth is another example in addition to water also, for which we observe a decrease in volume with increase in temperature for a particular temperature range. So, these are certain exceptions where alpha could go negative, or for all other substances alpha would always be a positive quantity. When so, what it does mean, just have a look. It does mean that in that situation delta P delta T constant V, which is equal to alpha by kappa, will be a positive quantity, and if it will be a positive quantity, what it does mean, the entropy will always increase with increase in volume, except for water between temperature range 0 to 4 Kelvin, except for bismuth, and except for antimony for a particular temperature range. Having said this, now what mathematical jugglery which we have been into, what we have achieved, it is time to look at that. Now see, we have evaluated two differential coefficients, delta as delta T constant, V as Cv by T, equation 19, and we have also evaluated delta as delta V constant T equal to alpha by kappa. So, basically ds, therefore, if we compare this equation 19, equation 30 and equation 12, which was the one which we had considered, that is the change in entropy as rate of change of entropy with temperature at constant volume times the temperature change plus rate of change of entropy with volume change at constant temperature multiplied by the volume change. So, basically if we compare this differential coefficient, should not we make use of equation 19 to write instead of this differential coefficient as Cv by T, and moreover we should also be writing delta as delta V constant T as alpha by kappa, making use of equation 30. So, what we get ultimately is the ds, the change in entropy, which is equal to Cv by T dt plus alpha by kappa dV. Now, let us see what is Cv. It is an experimentally determinable quantity. Once we know the nature of the system, temperature, a state function whose value we can get to know, initial and final temperature. Once we do get to know that, we can determine change in temperature also, we can determine the change in volume also, we can determine the expansion coefficient, we can determine the coefficient of isothermal compressibility kappa. So, when all these state variables are being related, so what we can do is we can determine the entropy change using the change in state variables such as temperature and volume under condition of constant pressure using equation 34. So, as a summary we can see that in equation 34, which relates the entropy change for any substance, that is in relation to temperature change and volume change. But a very important observation we can make over here, if you consider the volume change dV for liquids and solids, if suppose a substance which involve only condensed phase, if suppose in our system the substances which are present, they involve only condensed phase systems. So, it does mean liquids and solids. Whenever there occurs some transformation, unless pressure is very high, unless pressure value is very high, the volume change for these condensed phase systems is very small. So, it means dV value is very small. If dV value is very small, the contribution of second terms towards the entropy change would be very small. So, therefore, it as a conclusion we can say that except for gases, the dependence of entropy on volume is negligibly small in all practical sense. So, practically therefore, entropy is a function only of temperature for condensed phases. This observation can also be an answer, to an simple observation. You would have seen that in all textbooks where much of the emphasis is being laid on gaseous systems, work of expansion we do for gases, we make a model of ideal gas, we calculate the expansion work, we do all kind of calculations of gases. Why so? Because you see here also the entropy change expression which we have derived here, it involves two contributions, one due to temperature change and one due to volume change, and what we have observed is for condensed phases volume change is very negligible unless pressure value is very high, unless we require very sound specific calculated values. We would not like to calculate this second term, and we would only say for all practical purposes for condensed phase systems at usual pressure values, entropy is only a function of temperature only. Right. So, this is how we have developed an equation for a change in temperature and volume, that is if a system undergoes a change in temperature and volume, how we can calculate entropy change. So, we have developed such an equation. Now, that equation is being developed under condition of constant pressure. Now, question arises, can we also develop such equation which relate the temperature and pressure, that is under constant volume condition, because these are also the condition in which we do work. So, therefore, we need now to look at such conditions under which we can calculate the entropy change. And what is the, first of all let me highlight why it is very difficult to calculate entropy change under such conditions, that is when entropy is function of temperature and pressure. If we want to do that, then we want to consider first of all that entropy is a function of temperature and pressure. As we did for temperature and volume, we can also say ds equal to delta S delta T constant P dt plus delta S delta P constant T dP. Now, what we can do is we just in the same manner as we did for the earlier expression, that is the entropy change in terms of temperature and volume change, we can here also determine these differential coefficients. What way we can determine? Again we need to find some kind of an equation which relate this A and B with these differential coefficients whose value we can evaluate experimentally and we can determine there and the entropy change. But here there is a problem. If we compare this equation which we have envisaged for the entropy change in terms of temperature and pressure, if we compare it with fundamental equation of thermodynamics, there is no any variable change, like here there is a change in volume, here there is change in internal energy in the expression of fundamental equation of thermodynamics, but in the equation which we have envisaged for entropy change, there is change in temperature and change in pressure. So, what we need to do is we need now a double modification of this fundamental equation of thermodynamics, that is earlier we had to modify this equation only for internal energy, now we need to modify this equation for volume change also in order to express the change in terms of temperature and pressure. So, what way we do it? Just have a look. It is very simple basically. Considering the relation of enthalpy with internal energy, we have H equal to U plus PV. So, therefore, dH equal to du, we can differentiate this du plus P times dV plus V times dP. So, therefore, we can evaluate du as dH minus P dV minus V dP. So, therefore, what we get? This was the fundamental equation of thermodynamics, ds equal to 1 by T du plus P by T dV, and du equal to dH minus P dV minus V dP we have just evaluated. All we need to do is just put in the value of du from equation 38 in equation 11 and see what we get. If we do so, then ds equal to 1 by T dH minus So, you see here 1 by T instead of du, what we are writing in bracket dH minus P dV minus V dP plus P by T dV. Now, what way we can modify this? We can remove these brackets by multiplying each term with 1 by T, that is 1 by T dH minus P by T dV minus V by T dP plus P by T dV. If you see that P by T dV, two terms are common with opposite sign, and so these terms can cancel, and what we ultimately get is ds equal to 1 by T dH minus V by T dP. So, therefore, what way again we can modify this equation 40 by just envisaging the enthalpy change, the way we consider the entropy and internal energy change, that is dH equal to here Cp dt instead of Cv dt for du, here dH equal to Cp dt plus delta H delta P constant T dP. This is the equation we developed when we discussed the heat capacity under constant pressure condition. There we had discussed this equation and we had derived this also, the way we do it for internal energy just right now. So, it means we can substitute equation 41 in this modified equation, that is modified fundamental equation of thermodynamics, that is equation number 40. Here it involves the term dH. So, instead of dH we can substitute the right hand side expression in equation 41. So, what we will get is ultimately ds equal to 1 by T dH minus V by T dP. So, all we need to do is we need to substitute equation 41 in equation 40. What we get, ds equal to 1 by T C, for dH we can write bracket terms Cp dt plus dH dP constant T dP minus V by T dP. What way it transforms to? Ultimately it gives us, now you can see, it gives us, we can take all these bracket terms, we can collect dt terms separate and dP terms separate. So, now we have ds equal to Cp by T dt plus 1 by T minus V plus delta H delta P constant T dP. Now, compare this equation with that of the equation we had envisaged, that is ds equal to delta S delta T constant P dt plus delta S delta P constant T dP. Here this equation 35 has two differentials dt and dP. In this equation 44, that is modified equation of fundamental equation of thermodynamics, this also has dt dP. So, therefore, we can compare these differential coefficients which we had done earlier this way. And the first one is simply to evaluate, as we have done for the temperature volume when we had considered entropy as function of temperature and volume. The second one was very difficult, here also it is difficult, we will also do the same treatment, but that will be due for the next lecture. So, in this manner what we have done is today, by virtue of calculating entropy change in terms of change in temperature and change in volume, what we have done is basically we have derived an equation which we can make use of in order to calculate entropy change in terms of change in temperature and change in volume, which are the state functions. Now, if I remember, the last time a question was asked that as to how to calculate the entropy change for adiabatic processes. Students have this confusion in their mind that in an adiabatic process there is no heat being exchanged with the surroundings, so entropy change, what way we will calculate it. So, what I wish to say is we would make use of such formulas where the entropy change is related to state functions only. So, we will talk about it more in our next lecture. Thank you very much for the listening.
Thank you, Dr. Amit Kumar. Definitely we will have to take this up because we had a very intensive discussion today and we had so many calculations. But students, you can definitely go to our YouTube page and look at the lecture, and if you have any comments, suggestions or questions, please do write into us. Thank you.